Hey guys, so welcome to your very last video of this unit. One thing I'm going to explain really quick. I've mentioned before that I'm not really following the exact order of the book. So if you notice, if you go into the online textbook that I sent you, this is not part of chapter 1. I am calling it chapter 1, section 3, just so that you guys kind of know that this is part of the first blanket of information. I did provide the reading for you, but you're not going to find this reading in your textbook. So if you go into the textbook link and you try and find this reading, you will not find it. I have linked it for you on my website. Here are the things that I feel like you should know by the end of this video. You should be able to identify the 7 base units. You should be able to apply metric prefixes. You should be able to convert between various base units, and you should be able to distinguish between mass and weight. Some of these things are really obvious. You probably did them last year. I don't know how much you remember or how much you did last year, so I wanted to make sure we cover this. This stuff is really important. We may not focus a lot of it this year, but especially if you move on to chemistry, this will be super important. So it's really a good idea for us to just make sure we know it and we move on. Okay, so before we start the information or talking about the information, I want to kind of bring up some questions that hopefully will get your mind thinking and maybe you'll remember some of this information. So why is the metric system easier to use than the English system of units? And so our English system of units would be like feet, inches, ounces, things like that, compared to the metric system, which is like meters, kilometers, kilograms, grams, things like that. Why is scientific notation important, and why do we use it to represent small and large numbers? And then another question I want you to kind of think about is what units are used to measure length, mass, and volume in the metric system? So the first thing I'm going to tell you is that a measurement is a quantity that includes both a number and a unit. So that's really important. Whenever you are measuring anything in this class, you're always going to say, oh, well, the desk is 50 millimeters, and that's not right. That's not to scale, but I'm just kind of giving that out to you. You always have a number, and you'll always have a defining unit to actually quantify that. In science, the English system is not used, and the reason for that is because it's just so hard to convert from one thing to another, and it's not like consistent. So for example, 12 inches equals 1 foot doesn't correlate to anything else. In comparison to the metric system is really easy to follow because of the fact that everything is based on the number 10. So you're able to easily convert from one thing to another. So for example, there are 100 centimeters in 1 meter. And if you don't understand how I made that conversion, don't worry, because we are going to practice in class a whole lot, and I'm going to show some examples here. The first thing I do want to talk about is the SI base units. And so what the SI base units are is it's the International Systems of Units, and it's a system of measurements based on the metric system. So like I said, we're using the metric system, which are numbers of tens. And so the SI unit is based off of this metric system. The acronym SI is commonly used to refer to this system. So you'll always hear me say your SI units. SI units. We only do SI units. We will never do feet, inches, yards, nothing like that. So please don't even try. And this idea was adopted in about 1960. So all throughout science, it is consistent to always use the SI base units of measurement. So what I have provided to you here, this table, this is the SI base units. In this class, we are going to focus on using length, mass, and temperature. For the most part, we're not going to spend much time talking about time, amount of substance, electric current, and candela. Those are more used for chemistry and for physics. We will talk about length and the fact that we are going to be measuring different specimen and different concepts. A lot of things we'll talk about are very microscopic, so you'll need to measure the length of a cell, and it's going to be very small. We use the meter as our base unit. So that means that like 1 meter is the base for the length of something. The base unit for mass is kilogram. The base unit for temperature is Kelvin. We will convert all of these things in class, and like I said, we are going to practice quite a bit. So please don't worry if you're not understanding. This is just to give you the information right now. So the first thing you're probably thinking is, wow, this is a huge table. I highly suggest that you write it out, but I'm also providing to you a copy. So if you want to write this out and maybe add some notes to it, that would be awesome, because I am going to be talking about a few of these things. But don't rest assured, I am going to give you a clean copy that you will put on the front cover of your notebook. So you'll always have this. I do not expect you to memorize this. Do not memorize this. Now, the first thing I want to point out is that you have these things known as prefixes. And so what a prefix is it goes in front of a root word. It is the very first portion of the root word, meaning it'll tell you how much of something. So if anytime you see the word deci in front of any type of unit, then you should know that you're dealing with, oops, hold on, I got to grab my pen here. So I talked about deci. You should know that you are dealing with anything within the 10 to the negative ones place. Okay, so that would mean a tenth of something. A couple of other things. Like I said, I don't really know where you guys are at or how much you remember of this, so we are going to really take this quite slow. Giga, anything that is above this line here is a number that's greater than 1. So if you look at these exponents, this one, this one, this one, this one, and this one, you notice that the exponents are positive numbers. That means that these numbers are guaranteed to be large numbers, and they are guaranteed to be greater than 1. They will not have a decimal before the whole number. So for example, deca is 10 to the first. That means that it represents 10 of something. So if I were to say I have 1 decameter, that means I have 10 meters. Remember that your meter is your base unit. Okay, so everything is going to go back to that unit. So that is why it's represented by a 10 to the 0. Anything to the zeros place means 1. So 10 to the 0 means 1. So that's why you get 1 here. Same thing with hecto. Hecto, 10 to the second. That's like saying 10 times 10. That would give you 100. So 1 hectometer equals 100 meters. Like I said, I do not expect you to memorize this. I am going to show you a trick on how to move your decimal place so that you always know where to put zeros and where not to put zeros. Anything below this big line here that I told you, so all of this here, that means that it is less than 1. So if you want to write that in your notes or something, less than 1. So deci, centi, milli, micro, nano, and pico are all things that are less than 1. They are always going to have a point something, something, something. So for example, and also notice with all of these exponents, all of these exponents are negative values. Okay. So, like I was saying, for example, 1 decimeter equals 0.1 of a meter. Okay, so do you see how now I have that decimal in place? 0.1 of a meter. 10 to the negative second is 1/100th. So that's 0.01. It is now in the hundredths place. Same goes for a millimeter, micrometer, nanometer, and picometer. And like I said, we are going to practice this in class. Biggest things that I want you to come out with, anything below the meter is less than 1. It will have a decimal in front of the number. Anything above the meter is greater than 1 and won't have a decimal in front of the whole number. So this brings me to my next point about scientific notation. So I talked about meter prefixes in the last slide. So now I'm going to kind of bring that home and kind of talk about why it is so important to use scientific notation. So when we talk about a picometer, remember it's really, really small. Like it has 12 zeros before the whole number. So with that, it's 11 zeros. But anyway, it has a lot of zeros is what I'm trying to get at. To write that 20 different times in anything is super confusing, can lead to a lot of mistakes. And so what was established was the scientific notation. And this is a great way to express really large or small quantities without having to make a mistake. So like I said, used really useful in representing large and small numbers. Obviously, this number is super small. You know it's small because of the fact that it has all of these zeros before the 911. And there is a decimal place there. Anytime you see a number that looks like that, it's a really small number. In comparison to this really large number that has all those zeros after the whole number, so after the 911. Now, to write all those zeros, obviously, like I said, would be really confusing. So here's where scientific notation is really useful. You will always have a 3-digit number with a decimal and a 10 exponent. So what I mean by that is you'll always have 3 digits here that will have a decimal in between it. The next thing you'll have is you'll have a multiplication sign and then a 10 that has an exponent associated with it. Anytime you see a negative, this means you have a small number. Negative equals a very small number. When you see a positive, this means you have a really large number. Now, what I did here was I gave you an example. So these two are written out in full expression. Now, what I have done is I have condensed them to make them into scientific notation. So 9.11 times 10 to the 28th is the exact same number as 0.00000, and I don't know how many zeros are there, but there are quite a few. So I think there's like 27. But 0.911 times 10 to the 28th is the same as this very top first number here. Do you see how it's so much easier to say and to write if you do it in scientific notation? The second number here, this 9110000, the large number is represented by 9.11 times 10 to the 15th. So the negative 28, again, is a small number. The 15th is a large number. So right now, you probably don't have in front of you your SI base units of measurement table and your SI prefixes table. I happen to have one in front of me, so it's easier for me to look at. When we are in class, you will have one in front of you, so this will make a little bit more sense. Now, the first thing I'm going to point out is that if you look at my first example, 1 kilogram to 1 gram, we are converting from the base unit to a non-base unit. The base unit for mass is the kilogram, but a lot of times we're going to be using the gram. And if you notice, the kilogram has a K in front of the G. So the K is the prefix kilo. It's a prefix to represent 1,000 of something or thousandth. So what you're going to do is a lot of times I'm going to have you always convert to kilogram to gram. So you're going to convert from the prefix to the non-prefixed letter, if that makes sense. So if there is nothing in front of the number, that means it doesn't, or excuse me, the letter, the second letter, that means that there's no prefix to it. So 1 kilogram to 1 gram. So what you're going to do is you're going to look at your prefix table and you're going to move down until you get to the spot that does not have a prefix in front of it. So what I'm going to do is I'm going to move, and like I said, this is probably not going to make sense because you're not looking at the table, but I will show you this in class again. So you're going to move down until you get from kilogram to gram. Okay, so kilo to a non-prefix. When I move down, I've moved down 3 places. I've moved from a really large number to a small number. So kilo is much larger than gram. So I moved from a large to small. And I moved 3 different times. Whenever you move from a large prefix to a smaller prefix, you are going to move your decimal place to the right. So if you look at the first example, it says convert 1 kilogram to 1 gram. The decimal is after the 1. Okay, so even if there's not a decimal there, there's still always an invisible decimal. So it's like saying 1 point. It doesn't make sense to put the point there, but it exists. So I'm moving my decimal. I'm going from kilo to gram. So I'm going from a really large prefix to a smaller unit. So I'm going to move my decimal place to the right 3 times. 1, 2, and 3. What I fill in those humps is I put in zeros. So 1 kilogram equals 1,000 grams. Okay, so that's moving from a large to a small quantity. If you look at the next example, now I have you converting 5 grams to 5 kilograms. So now I'm going from a no prefix, a smaller quantity, to a much bigger quantity, a kilogram. So I am again going to take, I have 5 grams. I'm going to take my decimal, again it's at the end, and I'm going to move it 3 times. But now whenever I go from a small to a large, I'm going to move my decimal to the left. So your decimal goes to the left. This is going to be really messy. Okay, so small to large, you're moving your decimal to the left. Large to small, you're moving your decimal to the right. So here's my decimal, moving it to the left. 1, 2, and 3. Oh, I went over the page. See if I can move. Okay, so then I would fill my humps in with zeros and my decimals right there. Notice I moved my decimal place 3 times, but I only have 2 zeros. So that's a cool little trick. However many places when you're moving from a small to a large, however many places you're moving your decimal, you'll have 1 less zero. So I moved my decimal 3 times, I have 2 zeros. And that's just a way that I always use to check. So 0.005 grams, kilograms equals 5 grams. Okay, so that's converting. Now I want to practice a little bit of scientific notation. So write 0.000345 in scientific notation. Again, this is a movement of your decimal place. So all I'm going to do is I'm going to take my decimal. I'm going to write it a little bit bigger because I'm using my finger and it's kind of hard to write when it's that small. All right, so here's my decimal place, and I need to always get my decimal in between the first 2 whole numbers. So what I'm going to do is I'm just going to move it. 1, 2, 3, and 4. Now I'm at 3.45, but those decimals did not go anywhere. If you notice, the zeros are after a decimal point. If they are after a decimal point, that means you have to have a negative exponent. Now, how many? Now, that's just a matter of how many times you moved your decimal place. So I moved my decimal place 1, 2, 3, and 4. That means I am at the -4 spot. If I move my decimal 4 times, that is how much the exponent will be. Same concept goes for over here with your large number. So I'm going to take my decimal, which is at the end of the number. Remember, if there's no decimal in front of anything, or it's a large number. So I'm going to take it at the end and I'm going to move it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It needs to go in between the first 2 whole numbers. So now you're left with 8.67 times 10 to the positive 10th. Is that what I said? I said positive, right? Or I said 10. Hopefully. I'll do that again in class because I'm messing up here. So 8.67 times 10 to the 10th. I know that this is so confusing, and some of you probably really get this because you've done this last year. Some of you probably don't, or you just don't remember. We will go over this, and we will spend at least 2 days on all of this information. So please don't freak out just yet. All right, that's the end of this video. If you have any questions, please ask at the end of the video.